Hey everyone, Mini Macro Sound here. In my continuing journey of trying to write systems that let me pretend I'm doing homebrew on a game console without actually having to do all that work, I've spent many hours trying to make palette swapping work in GameMaker. You might say, well that's already a solved problem, isn't it? Yes, it is. Something that game consoles, before the advent of more than a gigabyte of RAM, did was the concept of sprite palettes. Graphics data was not stored with the color it should be. Instead, it was stored with the index of the palette it should use. When drawing sprites to the screen, you would specify which of the available sprite palettes it should use, and the console would draw the pixels to the screen with those colors. FCUX's PPU viewer here displays the sprite data with colors for visualization purposes, but in the ROM, they're stored as 2 bits. What appeals to me about this is the idea of sprites not inherently having any colors. This means that at any time, the program could change the palettes, and the sprites would change instantly and with no additional processing. That's something that's been kind of lost in modern game development, in my opinion. And instead, to emulate the same effects, we need to use shaders and other stuff. You might say, literally no one else has any problem with this. Correct! The common solution to this problem in modern games, and in GameMaker in particular, is a shader that takes a sprite that already has its base colors defined, and an image of the palette and which row or column of the palette to swap to, and outputs a correctly colored sprite. But there's a problem with this system. If you want to swap colors, you need to add a whole new row or column to your palette sprite, and generating textures at runtime is very costly. If you want to change any of the colors, perhaps in reaction to something in the game, you need to either have those pre-planned, which is hard to change later, or you need to keep generating palette textures at runtime, which is super heavy. So there's problem number 1, palette textures are inflexible. Another solution is a shader that takes a bunch of RGB values as uniforms for the colors on the base sprite to change, and a bunch of RGB values as uniforms for colors to change too. This works well enough and is a little bit more flexible, as you can simply change a variable in the code and it'll work. I like that. The problem with it, however, is that it's tedious to manage many input colors, especially if you're at all interested in doing full-screen palette swapping on a game with more than 4 colors. Additionally, sprites are still limited to 1 palette insofar as they still have inherent base colors. That's problem number 2. I don't think sprites should inherently have colors associated with them. Not only that, but actually managing this stuff, good luck if you want to have any kind of dynamic palettes. You either need a bunch of palette textures or massive unwieldy lookup tables. And speaking as someone who's been doing these kinds of effects for 4 years, I'm tired of that garbage. I want to restrict myself so that I can hide my artistic imperfections behind arbitrary palette limitations. Going back to the consoles I mentioned before, the only data stored about graphics is which index of the palette they use. The palette they draw from, and the color on that palette, is determined entirely by the program. Maybe the second solution isn't such a bad idea. What we need to do is figure out a way to use the RGB colors of sprites to direct the shader to a palette index. I think I've made that solution, and it involves color blending. Sprites in my system, for now, can have up to 31 colors on them and access up to 7 palettes of 31 colors each, for a total of 217 colors on screen at a time. Given that the NES palette only has around 55 colors on it, I think that's pretty good. The gray level of each pixel determines which index of the palette it uses, and the color blend determines what sprite palette it uses. Now before I show the second thing, I should give a flashing colors warning. Look away now if that's an issue. We're using the following blend modes to determine which of the 7 palettes the sprite uses. C white, C red, C lime, C blue, C yellow, C fuchsia, and C aqua. I'm sure you do. This is how the sprites get drawn to the screen. Obviously they don't look good, they're just using a grayscale palette with an image blend mode, but that gets rendered differently, and you'll see. I'm done with the flashing colors now if you want to look back. So here's my demonstration project. On the left is what's being drawn with the shader. On the right is what these colors are actually supposed to be. Right now it's just a randomly generated palette of 217 colors, and also the FPS, which is pretty stable. When we turn off the shader, we can see what's actually being drawn here, which is this white gradient sprite at 6 different image blend levels, and also white. And these image blend levels were selected because they have either 0 or 255 for all their RGB values, and that allows us to do math easily in the shader to determine which quote-unquote sprite palette we should be using. The first thing to point out with the code is how the palette is laid out. Because shaders only accept one-dimensional arrays as uniforms, we have to pack every single color into one array. To make the code a little easier to follow, I've actually split it into 3 arrays, those being the red, green, and blue values. But each one of those contains every color in one big line. That's a little hard to explain, so here's a visual demonstration of how this works. It goes from 0 to 255, then 0 to 255, then 0 to 255, etc., in steps of 8. And that's based on the quote-unquote gray value of the color. Since we have multiple sprite palettes, the first 0 to 255 is sprite palette 0, the second 0 to 255 is sprite palette 1, and so on and so forth. Remember how I said earlier that I used only blending colors with either 0 or not 0 as the RGB values? That means that a color on the screen will either be 0 or it will be one of our initial 32 gray values. Using this, we can say that R being not 0 represents a shift of 1, G being not 0 represents a shift of 2, and B being not 0 represents a shift of 4. Some of you may recognize that this is how bit shifting works. Now our palette has 32 gray values, so you can think of the shift as being 1 times 32, 2 times 32, or 4 times 32. Let's say we have this color right here. First, we'll need to figure out its gray value, which is one of the values that is not 0, so 120. Put a pin in that. Its position is here on the palette, but we've only figured out which index it uses, so now we need to figure out which quote-unquote sprite palette it wants to use. And if we want to make it use the sprite palette represented by the yellow blend mode, then we look at the yellow color that's on the screen, and we can see that its R value is not 0, its G value is not 0, and its B value is 0. That means we shift it once, and then we shift it twice. Now we know exactly which sprite palette we should source the final color from. Here's how the code for this works. I'm not going to go over the shader preamble stuff here, but know that we're setting up our uniforms and getting the color currently on the screen. First, we need to find the gray value. If we were to simply look for the value that isn't 0, like you might do visually as a human with your eyes, then the code would look something like this, and that's stupid. Instead, what we want to do is we want to get an average, because that value is either the same value as all the rest of the ones in the color, or 0. But if you simply divide it by 3, then the value will be wrong, since one of them may be 0. So this first line here adds 1 if R is not 0, 1 if G is not 0, and 1 if B is not 0. This results in a number that reflects how many values are not 0. Getting the average now is simply adding the R, G, and B values and dividing by the number we just got. We're not done with that number though. Now that we know the gray value, we can do the second step and find the palette index. First, since an RGB value goes from 0 to 1 in a shader, but goes from 0 to 255 in a normal color, we need to multiply it by 255. Then we divide it by 8, and this is just a constant I set up earlier. It's 256 divided by 32, which is 8. And that's since each gray value is 8 steps apart. This will make it range from 0 to 31, which is how many palette indices we have. Next, we do the shift that I mentioned earlier. I condensed it down to one line, but basically, we're adding a number to offset it in the line like we did earlier. We shift once if R is not 0, twice if G isn't 0, and 4 times if B isn't 0. Multiply that number by 32 and add it to the index, and now we have our final color. The extra check here is just so that we don't add anything if all 3 of the RGB values are not 0, since that means it's using the gray palette and we don't want to do any shifts. Finally, set the color to be the one that we obtained from the palette, and we're done. Once again, this solves 2 real problems. It's very flexible since the output colors are defined in code, and sprites have no real inherent color data since the only thing the gray is used for is telling the shader which palette index to use. And most importantly, this system's benefits are imperceptible to 99% of people playing the game. Any game programmer knows that some of these tricks are just for us. I've been Mini Macro Sound, and thank you for watching. Let me know if I should do more of this kind of stuff.